Okay, here's problem 328 in the problem solving videos. It says find V0 using nodal analysis. Again, we're going to follow along with the problem solving strategy on page 102 in the text. Here's our circuit. Notice that this circuit has a voltage source, and what we're going to do is let's identify the nodes. We have 1, 2, 3, 4. Since we want to solve for V0, let's pick the bottom node as a reference. And now what this gives us is a voltage source connected between two non-reference nodes. So we're going to have to use a supernode in this problem. Recall, when we have a voltage source connected between two non-reference nodes, we're going to be using the supernode to solve. So now, if we look, we have 4 nodes. So that means we have 3 node voltages. Okay, and our node voltages are V1, V2, and V0. So again, we're going to need 3 equations. Okay, so again, we're going to wind up writing 3 equations to solve for the node voltages. Okay, let's first of all start off with the constraint equation for the supernode. And remember, we get this equation by applying KVL around this loop. And again, let's remember what the polarity of those node voltages are. They're polarized plus to minus in this fashion, with the minus at the reference node. So if we apply KVL around this loop, starting here and going around clockwise, we'll have minus 12 plus V2, it's coming from this node to this node, minus V1 equal to 0. So we get our constraint equation, V2 minus V1 equals 12. And remember, we used KVL to get that reference node. Or excuse me, to get that equation for the voltage source. Okay, so there's the first equation. Now, we need 2 more equations. So let's go to our circuit. And again, let's show the supernode. And remember, we need 2 more equations. So first, let's apply KCL at that node. And if we do that, again, we'll sum currents leaving through resistances and set it equal to currents entering from sources. We'll have V0 over 1K plus V0 minus V2 over 2K equal to 0.002. And if we collect terms, this is the equation that we'll get. Okay, so there's our second equation. Now, to get our third equation, we're going to apply KCL at the supernode. Okay, so to get our third equation, we're now going to apply KCL at the supernode. We're going to do the same thing. We'll sum currents leaving the supernode through resistances and set it equal to currents entering from sources. So if we start, for instance, here we'll have V1 over 3K. Okay, that current's leaving. Here's another current leaving, that's V2 over 6K. Then we have another current leaving, V2 minus V0 over 2K. And that's all the currents leaving through resistances. We have a current source entering over here, so we get 0.008. And then we have a current source leaving, so we have minus 0.002. So there's our KCL equation. Now let's simplify that a little bit. It's 1 over 3K times V1 plus 1 over 6K plus 1 over 2K times V2 minus 1 over 2K times V0 is equal to 0.006. So there's our third equation. Now let's collect those in a matrix and go through and solve them using MATLAB. Okay, so in matrix form now, this is what we have. So there's our matrix. Notice that it's not symmetrical like it was in problem 3.3. And we have the following for the right hand side. You can see our constraint equation is the first equation up there. Using MATLAB, then we get the following. V1 is 0.8, V2 is 12.8, and then V0 is 5.6, and there is our answer.